Okay, hello everybody. Welcome back to the third lecture of Neuromorphic Engineering 2, which is going to be about MOS transistors 2 above threshold. But first I'm going to review subthreshold or weak inversion operation of the transistor. Then we'll look at some real subthreshold data, at least from the previous 1.6 micron technology chip. And then we're going to spend a long time considering superthreshold, also called above threshold or strong inversion operation in triode and saturation regions. This just refers to small drain source and big drain source voltage. The concept of the overdrive voltage and second order effects like velocity saturation and others. And then there's a useful concept called the specific current IS, which is the current at threshold. It's a simple idea which, once you have some basic parameters of a process, allows you to estimate on the back of the envelope the level of current at which you cross threshold. So you can estimate where you should operate your transistors. And then we'll spend quite a long time talking about drain conductance or the early effect by channel length modulation. And we'll talk about the intrinsic voltage gain of a transistor. And then we'll consider for a bit the second order drain effects, drain-induced barrier lowering, and impact ionization. So this is pretty hardcore transistor physics, not much neuromorphic engineering in it, but it's sort of critical for all levels of circuit design. So here goes nothing. So the idea this week is we consider strong inversion operation. So we have a transistor, I'll just draw a little cross section of it with a gate and then a drain and a source, or source and drain. And now what we do is we put some charge, positive charge on the gate, a bunch of it this time because we're going to go above threshold. And now the field lines don't just terminate on the fixed minus charges. These are mobile, by the way. But there's so much charge there that instead of terminating these field lines just on these fixed charges, you start to induce, coming from the source, you start to induce negative mobile carriers at the surface. And so the field lines start terminating on these mobile carriers at the surface. Now in subthreshold, you do have those carriers at the surface, it's like a vapor. But the key thing about subthreshold is that the concentration of these mobile carriers is much, much smaller than the dopant concentration in the substrate. So you can just neglect it. All the field lines essentially terminate on these fixed charges. But when you go above threshold, you start to have a concentration of mobile carriers in the channel that's bigger than this doping concentration, much huge. It becomes basically inverted. So it becomes N-type. And so now most of your field lines are going to terminate on the mobile charge instead. And so the key figure that you have to keep in mind when you're thinking about how all this works is the behavior of the surface potential. Let's draw that in red here, psi s, as a function of gate voltage. And do you remember how that is in subthreshold? Because of the capacitor divider, the surface potential increases. Let me draw that in red here. The surface potential increases linearly until you get to the threshold voltage, Vt. And then it kind of gets pinned logarithmically. And the slope of this is what? Everybody should be able to answer that that's kappa, right? That's what we calculated last time. But now we're talking about the mobile charge density, and let's draw that in blue here. That's like the density of mobile charge here in the channel per unit area. And how does that change as you change the gate voltage or increase it from 0? Well, I'll just tell you right now that in subthreshold, it increases exponentially. But on this linear scale, you can't even see it. We kind of scale the whole thing. So on the linear scale, all that 7 orders of magnitude of density increase just disappears. Now, as soon as you go above threshold, it stops being exponential and actually starts growing linearly. And the rate of change of that channel charge density is what? Cox. It's determined by this oxide capacitor here, Cox. So now the channel charge density just increases linearly with the gate voltage instead of exponentially. And so that's what we're talking about above threshold. And so then the above threshold current
is rather simple. When you have a small VDS, when VDS is approximately 0 or close to 0, then the current above threshold, or super threshold, is determined by the drift current. So now you have so much charge that the electric field can act on it and cause a drift current, and the current is going to be equal to the drift current equation, which is the mobility times the charge density times the electric field. What's the electric field? Well, mobility is related to the diffusion coefficient by Einstein relation, but right now we just treat it like a surface mobility, and the aversion charge is just Cox times the voltage you are above threshold, so Vg minus this Vt value. And what's the electric field? The electric field is just the drain source voltage divided by the length of the transistor. It's voltage divided by length. And we have to put a W in here too, because the wider the transistor is, it's kind of scaling the oxide capacitor. So this is per unit width. So we put a W in there. And then that results in an equation for small drain source voltage above threshold, where it's mu Cox W over L times V overdrive times VDS. And V overdrive, let me put that here. This V overdrive, too much coffee. V overdrive is just exactly how much the gate voltage is above threshold. And then we make a definition of this mu Cox W over L. We're just going to define that equal to some constant called beta. You see this all over the place when people talk about above threshold. So it's just beta times the overdrive times VDS. It's linear. Right? Does that make sense? It's linear in the gate voltage, and it's also linear in the drain source voltage. And now you have to ask, what happens in saturation? Remember, in subthreshold, the transistor saturates when the drain source voltage gets bigger than a few UT. It's independent of the gate voltage, right? It's just bigger than a few UT, because when the drain source voltage gets bigger than a few UT, then the ratio of forward and reverse currents becomes huge, right? As soon as you get a drain voltage that's above a few UT, the drain concentration basically goes to 0, and so you can ignore it. But what happens above threshold? Why does the current actually saturate with drain source voltage above threshold? Okay, so the way to think about that, the way I like to think about it, is by thinking about the inversion level at the source and drain of the transistors. So there's a picture on the slide you'll see later where we have a gate voltage. That's VG. And we also, above that, we have a threshold voltage. Let me draw that in a different color. This is VT. That's a threshold voltage for above threshold operation. Sorry, that's the source voltage here. This end. Okay, and then we have a gate voltage, VG. Okay, it's some overdrive above VT. So in that sense, the source is inverted by the overdrive. The source end of the channel is inverted by the VG minus VT overdrive. Does this make sense? Okay. So now you have a drain voltage. At what drain voltage do I need to put the drain so that the drain voltage is just at the threshold voltage? So let's copy this overdrive voltage over here. And if we put that here, there'll be some overdrive voltage. And let's just say the source is ground here. If this voltage is the overdrive, the drain voltage is exactly the overdrive, then you could see that the overdrive at the drain end of the channel, the drain end will just be inverted by the threshold voltage. So anytime the drain voltage is higher than the overdrive, the channel won't be inverted anymore. It won't be above threshold. Okay, so that tells you that the VD sat, the V drain sat above threshold is equal to the overdrive, which is the amount that you're driving the transistor above threshold. And so now you can get the saturation current above threshold. This is like the simplest approximation by just substituting this VDS, where the current saturates, into this equation. So if you take this saturation overdrive drain source voltage and substitute it in here, what do you get? You get the square of the overdrive voltage, right? It's just the overdrive, that's how much you're turning on the transistor. And VDS is the voltage at which the current saturates. And so ID sat is going to be equal to beta. And now you actually have to put in a factor of 1/2. That's because the curve actually saturates. If you plot VDS and IDS, and you'll see that that curves over and then saturates, and then there's the drain conductance part. Because of this curvature right here, that's why you get 1/2 if you do it more carefully. That's just beta over 2 V overdrive squared. That's the saturation current. So I apologize again for the terrible handwriting. Okay. So simple. And just simplify this equation up here. Just beta times V overdrive times VDS. That's what it is for small drain source voltage. And down here is what it is for big drain source voltage. It's basically what I'm going to tell you about above threshold today. Kind of all fits onto one slide, except for this part right here, which is the drain conductance part. It's a slope of this curve that's left over. And that comes from another effect, which I'm going to show you here in yellow highlighter. I hope it works. It has to do with this depletion region here, which I've exaggerated a lot around the drain end of the channel. As you change the drain voltage here and make it go up and down, or make it go up, then this depletion region is going to get wider if I increase it. And that makes the channel, effective channel length shorter. And if the channel is shorter, remember you have the 1/L here. If the channel gets shorter, the current gets bigger. And that's true in subthreshold and above threshold. And so we're going to look at some data from that. It's characterized by a certain intercept of this curve. Way back there on this x-axis, there's a so-called early voltage. That's where this linear extrapolation here hits the voltage axis. And what you're going to see, because this is a geometrical effect here, all this stuff here having to do with this saturation is a geometrical effect. You're going to see that if it just scales with the saturation current. In other words, if I make the saturation current twice as big, and above threshold, it's not going to saturate the same voltage, right? It's going to saturate actually at a higher voltage because of this overdrive. It should drop properly. It means that these curves, because it's a geometrical effect, these curves will tend to intersect at the same early voltage. And so the saturation drain conductance is also proportional to the current, just like the subthreshold conductance is proportional to the current. Okay, so that's a quick preview, or maybe not so quick preview of the stuff I want to show you today.
So let's review mechanisms of carrier transport. Carriers are holes or electrons, the majority carriers in this case, in the N or the P region. First mechanism is drift, which is movement of charge carriers due to an external field, electric field. And in this case, the current, I, is equal to the elementary charge times the carrier density N times the mobility. In this case, we assume it's a small electric field, so it's just the mobility times the electric field. And if you look at this band diagram here, with the electron energy up or the voltage down in case of electrons, the electron just goes down the band edge, because remember the band edge is kind of the potential level. And if there's a slope on it, that means there's an electric field. And so electrons go down it and the holes bubble up it. due to this external field. The second mechanism is diffusion, which is the movement of carriers due to a concentration gradient. In this case, the current is proportional again to the electric charge of an electron times minus the diffusion constant times the gradient of the concentration of electrons per cubic length cubed. And you can see it here. It's just symbolized by if there's a lot of electrons whizzing around here at the thermal velocity and few here, then there's a net movement in this direction. And just to remind you, there's a relation between this diffusion constant and this mobility by the thermal voltage through the Einstein relation. And as a review of subthreshold NFET operation, the current is diffusion current in this case, dominated by diffusion current. And it's controlled by the surface potential and the voltages at the drain and the source. And the concentration at the source end is exponential in this barrier height, barrier energy height. This theta S is the energy barrier, not a potential barrier, but an actual energy barrier divided by, well, actually it is potential barrier because it's divided by the thermal voltage, but it's theta S divided by UT. And just to remind you, the equations, once you compute the concentration at the source end of the channel, this is NS right here, and the drain end of the channel, ND right here, not actually in the drain, but at the drain end of the channel, as shown by these arrows here. Then you can get the concentration gradient by dN dZ. It's just NS minus ND divided by L. So here's where the transistor length comes in. If the transistor is longer, of course, the gradient is going to be lower for the same NS and ND. And if you work that out and work out how the barrier is controlled by the source and drain, then you get the current is, this is just the diffusion equation here, and the difference of concentrations with the length coming over here. Then you can get this exponential thing where the current is exponential in the psi s and then minus Vd and minus Vs. Now, to remind you also, there's an influence of gate on the surface potential through this capacitive divider, where you have a conducting region, the gate oxide, a possible inversion region, a depletion region, and the underlying substrate. And these form a capacitive divider where you have Vg here, and then there's a C ox for the oxide capacitance, and then there's a C dep for this extended depletion capacitor, and then psi dVg, which tells you how the surface potential changes when you change the gate voltage. It's given by C ox over C ox plus C dep, which is defined as kappa, which is a Greek kappa written like this. And then finally, if you put that together, you get the subthreshold NFET equation, which is that IDS is either kappa Vg over UT times the difference, either minus Vs over UT minus either minus Vd over UT. So you can see if you look at this equation, you can see the parts here that these first two parts here define the concentration at the source, which is the forward current if the drain concentration is 0, and then there's a concentration at drain, which is these two terms put together. It's all just saying the same thing here. It just says the current is a difference between this forward current and reverse current, which just combine linearly through this equation. And so then finally, the one equation that's used the most often of all, which is the simplest one, which is just the saturation current in subthreshold. The ID sat is the I0, the pre-exponential I0, times either the kappa Vg minus Vs over UT. Why is the kappa only multiplying Vg? Well, because this is just the thing that estimates what psi s is, the surface potential at the drain, at the source end of the channel. And Vs doesn't have the kappa because there's no gate capacitor. There's no capacitive divider. So this is the one equation you use over and over again in subthreshold to estimate saturation current. Okay, so what do those measurements of a subthreshold FET really look like. So here are some lab 2 results on subthreshold transconductance, it's transconductance because you're measuring IDS, the drain source current, versus the gate voltage, where the source voltage here is 0. So, and it's on a log scale here. So here's a picoamp, and here is a microamp. Right, so that's 3 orders of magnitude of current. This blue curve shows a subthreshold simulation, and these red crosses here are measurements of an NFET, which is 32 by 32 micron, N and P FETs, these 2 transistors, on the old class chip in AMIS 1.6 micron technology. AMIS 1.6 micron technology was a power CMOS technology aimed towards power electronics. Had options for high thick oxide transistors and so on to make power electronics like high voltage stuff. Anyhow, this particular transistor, you can see here that it's nicely exponential over at least, in this case, 6 orders of magnitude here, right? From a picoamp to a microamp, or even lower. And you can see that it then starts to curve over like this as the transistor starts to go into strong inversion. And by using the rule that you extrapolate the subthreshold curve and linearly on this log scale, and then when it becomes twice the actual measured current, you define that as the threshold voltage. You can see that VTN comes out to about 0.68 volts here, so 0.65 volts. That's the threshold voltage for the NFET. And then by extrapolating the curve down like this, here you can estimate that I0 for this transistor is 5 × 10⁻14 amps. Okay, so that is about 50 femtoamps, right? A femtoamp is 10⁻15. So the I0 is about 50 femtoamps. And what's V0? V0 is this exponential factor here, right? So in every V0 volts, the current increases by a factor of E, or 2.7. And you can see V0 here is 41, it's the slope of this curve, it's 41 millivolts per E-fold. You do the same thing for the PFET, and now what obvious thing that you observe is that the threshold voltage is much, much higher for these PFETs on this process. In other words, at the same gate voltage, the PFET makes a much, much smaller current, like 3 or 4 orders of magnitude smaller current. And so the VTP is way over here, close to 1 volt. And that means that the I0 here is only 2 × 10⁻18 amps. How many electrons a second is that? Would it be if you extrapolate this down here, 10⁻18 amps? Well, an electron is 1.6 × 10⁻19 coulombs. So this means that the I0 here is only about 10 holes per second. Now, of course, that's through the transistor from drain to source, but the leakage currents from the source drain to the substrate are going to be probably much larger than that, hundreds or thousands of electrons per second. But you see V0 here, the exponential scaling factor is 37 millivolts per E-fold. It's close to the value. It's hard to say why these V0s are different because you expect the oxide thickness to be identical for these 2 transistors. So I can't say why the measured V0 is different for these 2 transistors, but this is the kind of characteristic you would see. Now the next measurement that you were asked to do, at least in the past, was to measure kappa. So let's take a look at those results. So here are lab 2 results on the back gate coefficient kappa from the source follower circuit. Remember, this is a circuit where you set up the source follower, actually with the source current being determined in this lab by the source measure unit as a constant current, and then you sweep the gate voltage and look at the source voltage. And from the slope of that curve, source voltage versus gate voltage, you can directly measure kappa P and kappa N. And you can see that here in the source follower, because the current is constant, it means that for the top transistor of the N-type source follower, kappa Vg minus Vs is going to be constant. Therefore, kappa, just by differentiating, is just dVs dVg. How fast does the source voltage change when you change the gate voltage? And so the NFET kappa at a gate voltage of 1 volt is about 7.2, and then it rises up to a maximum at 5 volt gate voltage of about 0.84. Now, the gate voltage is very high here, 5 volts. Does that mean this transistor is above threshold? No, because the current is constant. It's just a subthreshold current. That means the inversion level of the channel is basically constant. But why does kappa change here? Why does it increase for both NFET and PFET? And why are they different between NFET and PFET? Well, think about that depletion capacitor again. As the gate voltage gets higher and higher, that means the depletion region gets wider and wider, right? Because the new charge that you add to the gate has to be balanced not by charge in the depletion region, but by new charge that's added at the edge of the depletion region, new fixed ions. And since those new fixed ions are further and further away, the capacitance becomes smaller and smaller, the incremental capacitance. And if the capacitance of the back gate becomes smaller, that means the capacitance of the front gate becomes more influential in controlling the surface potential. So in other words, the gate is better at controlling the surface potential, and so kappa goes up in this way. And you can work all this out from the CV relationship for a depletion capacitor. It goes kind of as the square root of the voltage. But it doesn't change much. This is general characteristics, 0.72 to 0.84. That's about 10% change in kappa. And it's the same for the PFET, but PFET, you see, has a higher kappa. What does that mean for the PFET? Well, higher kappa means wider depletion region, right? And so what it means is that the N wells here are more lightly doped than the P wells that the NFETs are sitting in. So the N wells are more lightly doped in this process than the P wells. So that's how you interpret this kind of curves. Okay, so now let's go to the main subject, which is the regime of operation above threshold, a strong inversion regime where the current flows through drift instead of diffusion, as it does in subthreshold. So, to understand strong inversion operation, we must understand how mobile charge density in the channel here depends on the gate to source voltage. Why is it gate to source voltage? Because the carriers in this transistor are always coming from the source. Unless you shine lots of light on the thing or it's very hot there, and they can be thermally generated. Otherwise, all the electrons that flow through this transistor are going to come from the source. So it's gate to source voltage that still matters. So let's consider it again in terms of this depletion capacitor with Cox and Cdep determined together what's happening here at the surface. So again, we have to look at the MOS capacitor structure, where we have here the gate, the gate oxide, this depletion inversion region, and the substrate. And in inversion, the mobile electrons, which are indicated by these bubbles here, are induced at the surface, and the surface is inverted. It becomes N-type instead of it starts as P-type, but now it becomes effectively N-type with mobile electrons. And the threshold is when this mobile charge density here is equal to the doping density. That's another definition of threshold voltage. There are many different ones. And this happens when the gate voltage or the gate to source voltage is bigger than the threshold voltage. So let's look at the MOS structure and inversion more quantitatively. Again, you have the gate oxide, the insulator, a possible inversion region, a surface potential. But now we're going to add these new terms, the QG, QI, and QD, which are the charge densities. So the QG is the gate charge, QI is the inversion charge, which we didn't have before in subthreshold, and QD is the depletion region charge. And in subthreshold, changes in the QG, changes in this gate charge due to a change in VG, are balanced by the change in the depletion charge, QD, this charge here. But in superthreshold, changes in QG are balanced by changes in the inversion charge, QI, at the surface. So it's always true that the gate charge is equal to the sum of the depletion charge plus the inversion charge. So what do these charges look like as a function of voltage? all the way from weak inversion through strong inversion. So here is a cool, interesting curve, which is for an end-fed, psi s, and which is the surface potential, and qi, which is the inversion charge, versus the gate source voltage. So the red curve here shows the inversion charge, and the blue curve here shows the surface potential, psi s. So by definition here, the inversion charge is 0 when the gate voltage is below the threshold voltage. Actually, you know, the inversion charge is increasing exponentially, but on this linear scale here, the inversion charge is essentially 0. And then once you go above threshold, what happens? Well, the inversion charge just essentially grows linearly. You're just adding new charge to the surface, and you can see that Qi is just going to be Cox, which is the oxide capacitance, times Vg minus Vt, which is by definition called Cox times V overdrive. This overdrive is just the distance the gate is above the threshold voltage when the source voltage is 0. This blue curve here shows the surface potential as a function of gate voltage. That's the curve you saw last week, right? In this case, psi s is just psi 0, it's some built-in potential barrier, plus kappa times Vg. And so it just grows up like this. Actually, it should be a slope less than 1 if these psi s and Vg are on the same scale, because kappa is less than 1, right? So imagine the slope is actually less than 1, but it just goes linearly, almost linearly. Actually, it gets a little bit steeper, right? Because kappa gets bigger as the gate voltage gets bigger. But anyway, it's basically almost a linear relation. And then once you cross the threshold voltage, instead of the surface potential increasing above threshold, the surface is pinned. It's kind of stuck. And what you actually can see is if you compute it, this psi s grows logarithmically with voltage. What's growing linearly is the inversion charge. So keep this in mind here because it kind of encapsulates what's happening all the way from subthreshold to superthreshold for the surface potential and the inversion charge. I was always curious why there is an abrupt threshold like you just saw. Why is it so steep, this transition? And the reason, again, has to do with the Boltzmann exponentials. The relations that the Fermi-Dirac distribution, which turns into a Boltzmann distribution. So again, this is the structure that you just saw before, turned on its side. Here's the gate. Here's the charge that you put onto the gate oxide, and here's the substrate with its fixed ions, this depletion region, plus the mobile electrons. So now you're already above threshold a bit, and there's some inversion charge. And below is showing the band diagram, showing the edge of the conduction band and the valence band, the intrinsic level and the Fermi level. So now the gate is above threshold, so you put a positive voltage on the gate. That means the energy for electrons on this side is low, right? That's why the band edge in this metal region over here is low. And because of this depletion charge here, there's a band bending of the conduction. This is just the integral of this electric field, right? The electric field here is 0 out here. And as you go through this depletion region here, the electric field increases linearly, kind of like that triangle tent. You integrate that once and you get a quadratic. So that's why the band edge of the conduction band is bending down. Now, you see here what happens as the band edge, the conduction band here, crosses the Fermi level or gets close to the Fermi level. The concentration grows by a factor of E for every thermal voltage as the band edge nears the Fermi level. And this complete range here is hundreds of millivolts, this band bending here, but all the action here happens every 25 millivolts. So that's why over a scale of 25 millivolts or so, the concentration of mobile carriers at this band edge here in the conduction band grows exponentially. So that's why you get this abrupt transition between subthreshold and superthreshold, which happens over a range of a few tens of millivolts, as the mobile carriers kind of bubble in from the source to fill up the surface. So now let's calculate the above threshold current using the fact that there's an inversion charge Qi, which is indicated by this green rectangle triangle here. Again, you have a source, gate, and drain voltage. These are N plus regions sitting in a P minus substrate. There's a depletion region around the whole structure, source and drain, and in the channel. And the transistor has a length L and a width W. Why is the inversion charge here shown as a triangle? We're assuming here that the drain voltage is bigger than the source voltage. Well, in subthreshold, we assumed that the depletion region was pretty much uniform, right? And there was no mobile charge compared to the concentration of depletion region, fixed carriers, fixed ions. But here we assume there's an electric field along the channel, right? Because that's what's making the carriers change, right? So that means in above threshold, the surface potential actually changes as you go along the channel. And that means that the inversion charge concentration actually changes as you go through the channel. It's heaviest at the source end, and then it grows smaller at the drain end, and even to zero at the drain end if the transistor is in saturation. But now to calculate the above threshold current, we're going to start with the simplest situation where the drain to source voltage is small. So here's the above threshold small VDS current. Well, it's just the drift current. So the drain source current is just the mobility times the actual charge density times the electric field. And now we can just write that down. It's a very simple equation. The drain source current is the mobility times the width of the transistor, because the wider it is, the bigger the current, times the charge density. What's the charge density? It's the oxide capacitance times the overdrive, VGS minus VT, times the electric field. What's the electric field? Simple. It's just the drain source voltage divided by the length, right? Voltage divided by length is electric field. And so now if you take these parts and write it out in the more traditional form, you get the familiar relation that the drain source current is a mobility mu Cox W over L, put the W here, times VGS minus VT times VDS. So another way to write it is maybe easier to remember. It's mu Cox W over L times the overdrive, that's this term here, times the drain source voltage. And this is the situation when you have a small drain source voltage. What about big drain source voltage? Well, first let's look what that is. The above threshold, strong inversion, linear or triode or ohmic characteristics. This is all referring to small VDS. In this case, if you plot the IDS versus VGS, you see that it's zero. Actually, it's increasing exponentially here, right? Just like you saw last week. But on this linear scale here, it's basically zero. And then as you go above threshold, the current increases linearly with the gate source voltage according to the multiplicative constant mu Cox W over L times VDS. So it's linear in VGS and VDS. Simple, right? Okay. So what about saturation? Saturation in strong inversion happens when the drain goes into subthreshold. Or another way that is more traditional is to call it when the drain pinches off. But we won't talk about that view here. So the drain current saturates when the concentration at the drain end goes to zero, just like it does in subthreshold. And saturation occurs whenever the drain end of the channel is at or below threshold. So let's look at it as a kind of a picture here. Here we have voltages in this picture. We have the source voltage, we have the gate voltage, and we have the drain voltage. And this is the threshold here. So right now in this particular situation, the threshold voltage is here, and the gate is above threshold by the overdrive, right? And the drain is at this voltage here. So the source end of the channel is inverted by this overdrive, because here you have this much overdrive at the source end. Okay, so now if we take this overdrive and put it at the other end, right? This is the same voltage here, just put down here. We can see that when the drain voltage reaches this overdrive, then at that point, when VD equals VO, which is the overdrive, the drain is at threshold. So this is the saturation voltage, because at this point, the gate is exactly above the drain by just exactly the threshold voltage. And that defines the saturation voltage. The saturation voltage for the drain source voltage is just exactly this VGS minus VT overdrive. So now we can estimate the above threshold saturation current. In the triode region, we had the equation we saw before. And now what we can do is we can replace this drain source voltage by the saturation voltage, which is VGS minus VT. And now you have two factors of VGS minus VT, right? And then we put in a factor of 1/2 here to account for the fact that the curve is curving over. And we find that the saturation current, IDS sat, above threshold, is just given by mu C ox W over L over 2 times the square of the overdrive. Okay, so one factor, this is important to remember. It looks like a square relation for the gate source voltage, but one factor comes from the charge density, right? VGS minus VT. That's kind of the inversion, the QI, inversion charge, and the other factor of VGS minus VT comes from the voltage at which the drain saturates, which is also the overdrive. Okay, I hope that's clear. Okay, so that means in saturation, the above threshold current is going to be a line if you plot the square root of the current versus the gate voltage. And so the slope of the IDS versus VGS above threshold is going to be of the square root here is going to be the square root of mu Cx over 2 times W over L. So again, it's easy to see if this is correct or not. You just plot it as a line because it's easy to see. You plot the data in this way, and then if it deviates from linear, that shows you how non-ideal the simple above threshold theory is. Okay, so let's review the regimes of above threshold operation, which is the dependence on VDS. So in the triode linear ohmic region, I current is mu Cx W over L times VG minus VT times VD minus VS. And now what you do is you take this constant here, which just depends on the geometry and the process parameters, mu Cx W over L, and you call it something called beta. Beta is just mu Cx W over L. And so now the simplest form of above threshold transistor equation is beta over 2, I equals beta over 2 times Vg minus Vt squared. Right? Nice and easy. So here, what does that actually look like? The above threshold NFET curve, I versus VDS, looks like this. So this is a saturation region, right? So here you have the ohmic region on this side, and here you have the saturation region on this side. And these are for different gate voltages, right? 1.25 and so on. Here's the equation, here's the setup here. And now you can see, in contrast with subthreshold, where saturation happens always at the same VDS, above threshold, the saturation happens at different voltages. Remember, the saturation of the transistor is a function of the gate voltage. It's the overdrive. And see, as we increase the gate voltage, the saturation happens at higher and higher voltages. And the current here, if you plotted it out, would be like square law with the gate voltage. You see how the curves are getting further and further apart on this linear scale because of the square law relationship. If you plot the other one, the other curve, which is I versus VGS, IDS versus VGS, we have this curve we had before. In subthreshold, it's linear on this log scale with the gate source voltage, and then it goes into square law. And then we have the threshold voltage by the same definition here of this factor of 2 from the extrapolated curve. And the threshold voltage is the voltage where the measured IDS is half of the IDS computed from the extrapolated exponential. Now, let's talk about something which is a little bit tricky, which is how the threshold voltage depends on the source voltage here. So actually the threshold voltage depends on the source voltage because carriers come from the source in the transistor. So as the source voltage increases, the threshold voltage increases even more because of the capacitor divider from gate to channel to substrate. So we can define something called VT, which is the effective threshold voltage. The effective threshold voltage, VT, is the threshold voltage at a source voltage of 0 plus Vs over kappa. So this factor here, 1 over kappa, is bigger than 1, right? So that means if VT0 here, the built-in threshold voltage, is 1 volt and kappa is 0.8 and Vs is 1 volt, the source voltage, that means the actual threshold is going to be 1 plus 1 over 0.8, which is 2.25 volts. This is a threshold voltage relative to ground, right? So all this says here is that this threshold voltage defines the VT that you put in VG minus VT. It's now the Vs is built into the threshold voltage. So the inversion charge here is going to be Cox times Vg minus Vt, where Vt is actually a function of the source voltage. If you actually write it out, it becomes like this. Vg minus Vt0 minus Vs over kappa. And sometimes you need to use this to estimate the actual threshold voltage as you go above threshold. Okay, so now let's consider the meaning of kappa in weak and strong inversion. So in weak inversion or subthreshold, kappa is the efficiency of the gate in controlling the surface potential. But above threshold, in strong inversion, 1 over kappa is the efficiency of the source in raising the threshold voltage. That's another way to look at kappa. Okay, so now I'm going to go through a rather tricky calculation of computing the above threshold current in the ohmic region more exactly or more formally. And this whole computation relies on computing the charge concentration in the channel and at the source end and drain end of the channel. So QS and QD are the charge inversion charge concentration levels at the source and drain end of the channel. The transistor has a length L, and again we're going to use this psi S here, Vs, Vg, and Vd. So if we can compute the charge density, QS and QD, at the source and drain end of the channel, then we should be able to compute the current using the drift equation, if we can compute the electric field. So let's see how this calculation goes. So this goes over 2 slides. So we start with the drift current equation, where the current is mu times the charge density times the width of the transistor times the electric field. So now we're going to write the equations for the electric field along the channel, this Greek E. And so we have to use the channel capacitance. What's the channel capacitance? Channel capacitance is the rate of change of the inversion charge versus the surface potential, which we know is Cox plus CD, right? Why is, so that's just by definition, right? The channel capacitance is the sum of the oxide plus depletion capacitance. And that defines the rate of change of the inversion charge with psi S. We also know that the field in the channel, electric field, is minus d psi S, dz. dz is along the channel. So the derivative of the potential along the channel is just exactly the electric field. So combining these two equations, 1 and 2, we can find out that the electric field along the channel is equal to minus 1 over C times dqi dz. So we want to get the electric field here. So how does that come about? Let's look at these two equations again. So here's d psi S, right? So if we put this together, we see d psi S is dz times the electric field. Right, so it's just combining these two things together. We find the electric field is the 1 of the capacitance times the derivative of the inversion charge along the channel. So now we can go back to the drift current equation again. I is mu n times qi times w times the electric field. Now we've computed this electric field, and it's a function of qi. You see that here? So we substitute equation 3 back in to the drift current equation, And then we get the I is mu times Qi times W times 1 over C dQi dZ. And now we observe that, this is the tricky part here, we observe that Qi times dQi dZ is actually the derivative of Qi squared along the channel. So d dz of Qi squared is exactly dQi dZ times Qi. That's where we get the 1/2 too. Right? Because when you differentiate this, you get a 2 times dq dz times q. Okay, so now the non-intuitive part is we integrate this from the source to the drain into the channel. So we integrate 4 along the channel from the source to the drain. And since the channel has a length of L, we get I times L is on the left side. And now we integrate this from the left to the right side of the channel. All we have to do is evaluate this, right? So if we integrate the derivative of Qi squared from the channel, we just get Qi squared. So then we find out that I times L is W times mu n over 2C times the difference of the square charge density at the two ends of the channel. Okay, so now if we can compute Qs and Qd, we can compute the above threshold current. So that's done on the next slide. So this is what the previous slide computed here. So we have to compute Qs and Qd. Well, we computed that before. That's the inversion charge density, right? It's just Cox times Vg minus Vt0 times minus Vs over kappa. This is the effective threshold voltage here. And similarly for Qd, we get a similar expression where kappa is Cox over Cox plus Cdep. So we just substitute this Qs and Qd into the equation here, and we find out the complete above threshold equation. It's a complicated equation, but if you rewrite it to bring the kappa outside, you get this expression down here. It's mu Cox W over L over 2. Then there's a 1 over kappa in front, and then there's a kappa here, which cancels. You see it's Vg minus Vc0 minus Vs, so it's still a kappa Vg minus Vs squared. And if we simplify that whole equation down to just make Vs equal to 0, then we get the equation that we showed you there for above threshold, ohmic and saturation regions. So this is the more complete equation for above threshold operation, which is computed by this sort of indirect method of integration of the electric field along the channel. See if you can replicate that calculation for yourself. So if you set the if you take that previous expression and you set the drain concentration at 0, in other words, you go above saturation for the drain voltage, and then you get the equation that I is just IF here. It's not really a linear combination of the forward and reverse current anymore, but you take this equation and set Vs equal to 0, and you find out that the drain current is exactly beta over 2 Vg minus Vt squared. So beta over 2 times the square of the overdrive voltage. And so it matches what we calculated kind of intuitively before. You must realize that every one of these equations is really an approximation to reality. Real operation is much more complicated. Okay, so what about above threshold PFET? So you have the same situation here, except that the PFET has P source drain region sitting in an N well. And the carriers are holes, which go from the, in this case, they bubble up under the barrier from the source to the drain end. And there's mobile inversion charge of these holes in the channel. And everything works the same except all the voltages polarities are flipped in sign, and the reference voltage for all the voltages is the N well. You don't care about ground substrate voltage at all. Everything is relative to this local substrate N well. Otherwise, it's exactly the same equations. So now I'm going to tell you about the concept of the specific current IS. The specific current is defined as IS equals 2, not a half, 2 times mu Cox WRL times the square of the thermal voltage. So it's 2 beta UT squared. That's just the definition of specific current in the paper in Analog Integrated Circuits and Signal Processing 1995, Christian Enns, Krummenacher, and Eric Vitos. three famous people in CMOS IC design, who I'll tell you some stories about later. But anyhow, this IS is approximately the current at a gate overdrive of the thermal voltage. Basically, you're operating the transistor sort of above threshold, but just barely above threshold by the thermal voltage. So it connects subthreshold and above threshold through this above threshold equation, but at a subthreshold overdrive. So this current is a working definition of the border between weak and strong inversion. It's sort of the middle of moderate inversion, which is the complicated region in between those two other ones. And knowing the beta and the VT, you can estimate IS, which is very useful for a designer to know where a transistor will be working given a current. By where a transistor will be working, where in subthreshold or above threshold or moderate inversion the transistor will be working. So for an example, you can compare with the data that was shown from the Lab 2 experiment. If the mu-n is 400 centimeters squared per volt second, and the C-ox is a femtofarad per square micron, and the W over L is 1, then we can estimate that the IS is 2 times 400 centimeters squared per volt second times the W over L. Well, we have to convert here from centimeters to meters, right? We do that with this conversion factor. And then we have to calculate the oxide capacitance. It's a femtofarad per square micron, which is 1 e minus 6 meters, times the square of the thermal voltage is 25 e minus 3 volts squared. And we find out that's 50 nanoamps if we calculate this all out. So the specific current in this particular process for N FETs with this N mobility is going to be 50 nanoamps. Now, how does that compare with the measured data? Let's look in the next slide. So here is the measured transistor current that we saw from the Lab 2 experiment. We can see here that the level of current in the N FET where it goes above threshold is about about a fraction of a microamp, right? But if we actually calculate the specific current in this process, it's about 50 nanoamps. And so it's close to what we estimated, what we actually measured. Given the, so we calculate the specific current given the mobility and the oxide thickness and so on from the process parameters that we look up for the process, and then we actually compare it with measurement, and it's close to the measured result. And you see the current as you go above threshold is the same for the N and P FET, right? Because the mobilities are almost the same for the electrons and the holes. It's a little bit smaller for the P FET because the mobility is smaller. But it kind of matches up with what you estimate. Okay, remember the mobility is actually a function of the electric field. We assume the mobility is constant here, but actually you see it's only constant when the slope of this electron velocity versus electric field, the slope here is only constant when the electric field is small. Once the electric field gets big and the velocity that the electrons or their holes pick up between collisions becomes comparable to the thermal velocity, then this is no longer true, right? And eventually, if you make the electric field big enough, then you get this effect called velocity saturation. And so that affects the above threshold current. And so if you really make a big electric field, a big drain source voltage or a big gate voltage, then the square relation is no longer true because the mobility is no longer constant. It gets smaller and smaller. And so what happens then is that ID sat becomes linear in the gate overdrive when velocity saturation limits it. And so again, here is the velocity of the carriers versus electric field. And it deviates from linearity when the electric field gets big enough. So when the channel is short and the field is high, this is what happens in logic circuits. When the field is high along the channel, then carriers saturate at thermal velocity. And then the saturation current is then linear in the overdrive. So for small, overdrive, or in small drain source voltage, then the saturation current goes like the square of the overdrive. But when you make the gate voltage really big, then it becomes more linear with the overdrive. So that's velocity saturation. Okay, now let's go to some very important subject, which is the drain conductance, also known as the early effect or channel length modulation. And it's named after this fellow named Jim Early from the bipolar transistor era, who discovered these length modulation effects in vertical bipolar transistors and wrote made it clear for everybody how it worked. And what you observe here is that the drain source current as a function of the drain source voltage is actually not constant like we assumed before, but it's linear with the drain source voltage. And if you take these currents versus drain source voltage for different gate voltages and extrapolate them until they intercept the voltage axis back here, they kind of come together at a common point, which is called the early voltage. So it's like the drain conductance, which is the slope of this curve, is kind of proportional to the drain saturation current. So what you observe is that the drain source current appears to have a finite conductance. This conductance is proportional to the saturation current. So the bigger the current, the bigger the conductance. And it comes from channel length modulation induced by drain voltage changes. And so let's calculate this formally, and then we'll try to understand it. So the early effect channel length modulation calculation goes like this. You have a transistor. It has a particular physical length, but it has an effective length, LF, which is reduced by the amount that the drain depletion region changes with the drain voltage. And so by definition, the drain conductance is the rate of change of the drain current with the drain source voltage. So we can rewrite this to bring out the effect of this effective length here. We can say di dVds is di dLF, so it's the rate of change of the current with the length, times the derivative of the length with respect to drain source voltage. See these parts cancel out here, these partial derivatives? And so now we know that the current is proportional to 1 over length, of the 1 over length effective of the transistor. So now we can directly calculate that the di dLF is equal to minus I over LF. Why is that true? Well, because if you differentiate this current with respect to 1 over L, then you get 1 over L squared, right? But 1 over L of that is already the current, because the current is proportional to 1 over L through the either the electric field along the channel or the gradient density, the density of the gradient. So you already know from both basic transistor equations that di dLF is minus I over LF. Okay? So you can take that and put that back into here and you say the drain conductance is minus I over LF times dL dVds. Now, if you assume that the rate of change of this depletion region here, or the derivative of this length here, LF, with respect to VDS is constant, then you can say that the drain conductance is I over VE, because this is just a voltage here, right? Derivative of voltage with respect to effective length, this cancels out here, and you can rewrite this that the drain conductance is just proportional to I over voltage. It's the drain conductance, right? It's the derivative of current with respect to voltage. So you now define this 1 over VE, this minus 1 over VE is the derivative of the effective length with respect to drain voltage divided by the effective length. The length cancels out here, so it has units of 1 over voltage. And then you can say that the current is equal to the saturation current times the drain conductance times the drain voltage. Or another way to write this is to say that the drain current is the saturation current times 1 plus VD over VE. So this early voltage here is where the curve intercepts the x-axis when you measure it and extrapolate the curve. Okay, so the key assumption here is that the current is inversely proportional to the effective length, and this dL dVds is kind of constant. It doesn't depend on VDS. So it's kind of in the linear region, a linearized region of the depletion region change with drain voltage change. Okay, so does that really work? Well, let's look at it. What those characteristics look like. So note how VE here goes like 1 over length. The longer you make the transistor, because the effect of the channel decreases as the effect of this channel length modulation decreases as you make the transistor longer. Right? It's just a kind of a fractional length modulation. So if you make the whole transistor longer, the effect of this small modulation of the length becomes smaller. And that's why when you make the transistor longer, the drain conductance becomes smaller. Okay, so by definition, the early voltage is where the drain current curve saturates intercepts the axis here. And actually, VE is not really constant with the drain voltage or the saturation current ID. It's just a first order approximation to reality, which is very useful for conceptual thinking and also hand calculations. So let's look at some real early effect measurements from 2015 measurements of this 1.6, it's actually 1.6 micron class chip. So here are the drain source currents versus drain source voltage for different gate voltages. And you can see the exponential increase in the drain current with gate voltage increase. Each increment of gate voltage here is linear. And now what they did was to take these saturation parts of this long transistor, 32 by 8 transistor, and they fitted a line through them. Okay, and way back here at minus 100 volts or so, these curves, these lines here intercept the voltage axis. Now you can plot this V early voltage in volts here, it's around 100 volts, as a function of this saturation current. And you see it varies from 40 volts up to 140 volts. But in this entire above threshold region here, you can see the voltage is pretty constant. It's around 140, 150 volts. So in this case, this early voltage approximation is pretty good. Although when you go below threshold, I'm not sure if this measurement is reliable. It appears that this early voltage gets smaller. And you must understand that all these phenomena are actually quite complex. They're determined by the three-dimensional electrostatics of what's happening at the drain end of the channel. But this kind of encapsulates the idea of the early voltage. Okay, I want to tell you about one more effect, or two more effects actually, Dibble and impact ionization. So there's a second order drain effect called Dibble, which Dibble stands for drain-induced barrier lowering. And it comes about because an increased drain voltage lowers the energy barrier by reaching through the channel all the way to the source. It especially occurs in short transistors, and the effect is that a large drain voltage decreases the threshold voltage by 100 millivolts or so. So here you can see the energy diagram of the band edge again at the source, channel, and drain for two different drain source voltages. This is small VDS, and so you have a potential barrier that looks kind of like this. But when you have a large VDS, the depletion region gets so wide that this actually reaches through all the way to the source, and it lowers the height of this barrier here. Right? So now normally it should be only the gate that controls the height of the barrier, but in this case the drain actually controls the height of the barrier too. And so you can observe this effect in this 45 nanometer process with an oxide thickness of 2 nanometers for two different drain source voltages, 1 volt and 50 millivolts. Here is the gate source voltage, ranging from 0 up to about 1.5 volts. And here is the drain current plotted on a log scale. And so what you can observe is for a small VDS, you get this nice exponential, and it looks like the threshold voltage is right here, right? This is where you get a deviation of a factor of 2. But when you make the drain source voltage big here, you see because of this Dibble effect, the threshold voltage actually drops, and so the current is much bigger than you expect by the basic theory. So that's Dibble. The second order effect I want to talk about is impact ionization. So in impact ionization only occurs if the drain voltage is high enough to give electrons the ionization energy. What you observe for impact ionization is that the drain current is larger than the source current. Normally it's exactly the same. And in impact ionizations, electrons gain enough energy when going through the depletion region at the drain end to create new electron hole pairs. The holes are pulled by the E field to the substrate then. So in summary, both dipole and impact ionization look approximately exponential in the drain voltage. So let's look at this impact ionization at the drain end of the channel. Here you have the gate, a depletion region, and here is the drain and the depletion region around it. So now, as the electrons, suppose this is an NFET, as the electrons go from the drain end of the channel into the drain, they pass through this depletion region with a high electric field. If the electrons can gain enough energy to create a hole, in other words, if they can gain the band gap energy, 1.1 electron volts, then they can actually knock into an atom and create a hole. And now the hole will be pulled in the opposite direction, right? But the hole actually won't be pulled into the channel, right? It'll be, remember, carriers go home. This hole won't go through the channel here. It'll just go straight into the substrate, right? Because a strong electric field here in this depletion region in the channel, that'll just pull the hole straight to the substrate. So what you observe, if you actually measure it here, and I have measured it with my own hands, is that as a function of drain source voltage, the source current might increase linearly with the drain source voltage. That's the early effect. But you see the drain current is bigger than the source current. And the difference gets bigger and bigger as you increase the drain source voltage. And you'll see this effect only takes place once you get above a drain source voltage here of maybe a couple of volts. So you can build up these impact ionization effects. Because you can't ionize unless you get enough energy, kinetic energy on the electron, so you can create this electron hole pair. Okay, that's all I'm going to tell you about above threshold transistor effects. Now, the last thing I want to tell you about is conductance. So this is what you use all the time in circuit calculations. So let's look at the subthreshold FET in saturation, e to the kappa Vg minus Vs over Ut. And let's compute the subthreshold gate transconductance. That's called GM, whether it's above threshold or below threshold. The gate transconductance is called GM, and it's defined as the change in drain current with gate voltage. If you go through this equation here, if you differentiate I with respect to Vg here, you just get back the same exponential multiplied by kappa over Ut. If you do the same thing for the source conductance, how much does the current change with the source voltage? You go through this exponential, characteristic of exponential. If you differentiate it, you get back the exponential again, and you find out that the source conductance is minus I over Ut. So this is really fundamental in subthreshold. The conductance is actually proportional to the current divided by the thermal voltage. Okay. And then the drain conductance will be GDS is ID sat over VE. So you see here, they're both some voltage, right? The gate transconductance is proportional to kappa over UT times I. This is around 25 millivolts. And the drain conductance is ID sat, it's the same I, divided by the early voltage, which is on the order of tens or hundreds of volts. So here you have a voltage that's tens or hundreds of volts, and here you have a thermal voltage. You can do the same thing for the above threshold NFET conductances. Right? That was subthreshold, so let's see what those look like. So in the saturation region, when you mostly care about this, you see that ID sat is beta over 2 times the overdrive squared, where beta is defined like this. And now let's calculate the above threshold gate transconductance. Again, you just differentiate with respect to the gate voltage here. When you differentiate this with respect to gate voltage, you get back just the overdrive. The 2 here cancels the 2 here, and you find out that the above threshold transconductance is beta times the overdrive. It's simple. That means that if you write it out in terms of current, the above threshold transconductance goes like the square root of 2 times the current divided by beta. So you don't have a nice simple relation between the gate transconductance, well, except that it's the overdrive here, right? And the drain conductance remains the same. Drain source conductance is ID sat over VE. Okay. So here you have the gate overdrive. Okay, so here's a quiz. What is the intrinsic voltage gain of a transistor? So what do I mean by intrinsic voltage gain? It means you make a perfect current source of value ID set as the load on the drain. So you build a circuit here where you have a single transistor, you put a current source which is sourcing exactly the saturation current of this bottom transistor here, and what you ask, what's the incremental voltage gain, A, which is D minus dV out dV in. Okay, so let's do that on the blackboard. And you can see there the result. Okay.
So I hope this is being recorded. So I'll reproduce the situation again. We have a transistor sitting here. Going into it is a current source, which has the value ID sat of this transistor. It's approximately the saturation current of this transistor. This transistor has a gate voltage of VG, and it has a drain voltage and equal to the definition of the output voltage, which is V out. And so now what we want to calculate, the question is, what is the gain A, which is by definition minus A. Let's just calculate the negative gain, because the gain is going to be negative, right? If I increase this gate voltage, that's going to increase the saturation current in this bottom transistor. If this current goes up and this current stays the same, there's more current being drawn out than put in, so the voltage is going to go down, right? So minus A is going to be dV out over dV in. And so the situation, if you look at it in terms of the drain currents of this transistor, is you can plot as a function of V out here, which is equal to VDS of the bottom transistor. You can plot the drain current of the bottom transistor. Let's do that, say in blue here. This is the IDS. And so you have the typical saturation. Doesn't matter whether it's below threshold or above threshold, but we'll assume that the output voltage is above the saturation voltage. So VDS is big enough. And then for this region above the saturation voltage, we're going to have a slope here, GD, which is the drain conductance, which remember you saw before. It's the saturation current divided by the early voltage. So that's your drain conductance. Now, fighting that out is the current in ID sat, right? So that's a kind of constant current here. It's an ideal constant current source where the current doesn't depend on the voltage. Now you can see that if you change the gate voltage, say make it bigger, you're going to get a bigger current in this bottom transistor. And that's going to make this go up more, and it'll have the same conductance, but it'll cross at a different voltage. So what we're talking about is if you change delta VG, what is delta V out? And so you can see here that it crosses where the currents are the same. They must be the same, right? It crosses at a much different voltage. And the flatter this curve is, you can see the more the voltage is going to change when you change the gate voltage. And so the way you model this is you use what we had before. You just model the transistor circuit as a combination of an ideal current source, which is the saturation current, which is ID sat, the bottom transistor. This is the load up here. And then parallel with that is the drain conductance, GD. And this ID sat here is equal to the GM, which is the transconductance, times VG. Okay, so you can kind of imagine what the gain is going to be of this circuit. It's pretty clear if you think about it for a bit that the gain is going to be the ratio of these two conductances. A is going to be GM over GD, which is equal to maybe something more familiar. It's GM times R out, because the output resistance of this circuit, and this thing has infinite resistance, the output resistance of the circuit, R out, is 1 over GD, which is also called G out. So, it's a product of a conductance times a resistance, or the ratio of two conductances. And so, yeah, we can now calculate this because we know what GM is, right? So let's do it for subthreshold. So for subthreshold, let's calculate the explicit voltage gain. A equals GM over GD, right? So what's GM? Well, we calculated before. It's just I times kappa, that's the gate trench conductance, divided by UT. And the drain conductance is I divided by the early voltage. Nice and simple. The I's cancel out here. And what you end up with is a nice, beautiful, simple expression. It's kappa BE over UT. And if we put in explicit numerical values, let's assume that kappa is 0.8. Let's assume the early voltage is, say, for simplicity, 100 volts. It's a pretty long transistor. And UT is 25 millivolts, which is 1/40th of a volt. And so you have 40 times 100. That's 4,000. That's 0.8. So you come out with around, say, around 3,000 or so is the voltage gain. It's a negative voltage gain, right? And that is a constant DC voltage gain, steady state voltage gain, all the way through subthreshold. But now what you'll find out if you work out what GM is above threshold, in subthreshold, it's kappa I over UT. It's just proportional to the current. But above threshold, you'll see that GM will go like the square root of the current. And so what you can see, it's quite cool actually. You'll see that when you go above threshold, in the top, you're going to have something that goes like the square root of the drain current. In the bottom, you have something that goes still like the current. And so square root of I divided by I goes like 1 over square root of I. So once you go above threshold, the voltage gain actually goes down like the square root of the current.
In reality, real transistor models for numerical simulation have many, many more parameters, actually hundreds of parameters. Here's an example of SPICE, the Special Program for Integrated Circuit Emulation. BSIM, that's the Berkeley simulator. Version 3.3 parameters. These are all parameters here which are affecting different second order and third order effects of current in the transistors. And the numerical simulators of the transistors have been banged on for decades after decade. And there's a whole big industry, $1 billion industry, to measure these parameters from working transistors and from process simulation in order to enable accurate simulation of the circuits. Because the process of transistor fabrication and chip fabrication is just open loop. You know, you kind of have a very well-controlled process which fabricates the transistors, and you have to be able to estimate beforehand from sample data, including the variances, how well or what characteristics the circuit will have after you fabricate it. And so all this kind of stuff is discussed much more in the second semester of the course, which is about IC design, and in all the real circuit design courses, where you just run these simulators with these model parameters and just hope that they're correct without really understanding all the details. So that concludes this lecture on this above threshold effects. And next week, Shichi will take over and she'll talk about some basic static circuits. This inverting amplifier, she'll review again, and then she'll go into basic circuits like a diff pair, a current correlator that takes two currents and computes the normalized product of them, and the bump anti-bump circuit. Interesting circuit. And perhaps she'll start working on things like the current mirror that copies a current from one branch to another, and that is used together with a diff pair to make the simplest transconductance amplifier that takes a difference of voltages and turns it into a difference of current that's scaled by your desired tail current or your bias current. It's been fun doing the first few weeks with you, and I'll see you later in the semester.